Okay, hi everyone, and welcome to this April MAP webinar. The topic of today's webinar is Climate Extremes, Understanding and Predicting High Impact Conditions. We're very excited about the 4 speakers we're going to hear from today. The order will be Kinsey Mo, who's at the NOAA Climate Prediction Center, and she's going to speak about flash droughts over the United States, identifying types of flash droughts. And that'll be followed by Scott Weaver, who's also at the NOAA Climate Prediction Center, and he's going to discuss the low-level jet, which is a meteorological feature in the central United States, and how that's related to regional tornadic activity. And then that'll be followed by a couple of talks that are going to focus more on Atlantic tropical cyclone variability and prediction. First from Gabe Vecchi, who's at the NOAA Geophysical Fluid Dynamics Laboratory, and he's going to talk a little bit about seasonal prediction and new prediction systems that they're working on at GFDL. And then finally, Chris Thorncroft from SUNY Albany, who will talk about Africa easterly waves and their relationship to variability in Atlantic tropical cyclones. And I'd like to mention also that this webinar is co-sponsored this month by the Earth System Science Program. So thanks to Jim Todd and Sandy Lucas for working with me to plan this out. So very excited about this slate of talks, and so we'll move to Kinsey first. Kinsey, are you on the line?
Yeah, I'm here.
Great. So I'm going to transfer control over to your computer and just share your desktop with everybody. While Kinsey's sharing her desktop, I'll mention that the way we run this is everybody on the line, except for the speakers, is muted throughout the webinar, and I'll send a solicitation out towards the end of the talks for questions, and you should type your question in, send it to me, and then what I can do is unmute your line, and you can ask it of the speaker and ask any follow-ups. So, start thinking about questions as the talk is progressing, and you can send them to me early. You can send them to me before the conclusion slide, and we'll queue you up to ask your questions. So, Kinsey, you ready?
Yeah, can you see me?
I can't see the screen, so you should go into WebEx and click that Share My Desktop button.
Okay, just a minute. Yeah, let's see. Okay, so.
Kinsey, are you in PowerPoint right now by any chance?
Yeah, I'm on. I can see your screen, like a desktop, topic, climate. Yeah. Okay, I'll share my desktop.
There you go. Great.
Can you see me now?
Yeah, I can see it. So just bring your slides up and then take it away.
Can you see me?
Yep, looks good. So go ahead.
Okay, good. All right. I'd like to talk about the flash drought over the United States. And this is work in collaboration with Dr. Dennis Latimer from University of Washington. Flash drought considered as a high-impact event because it's always happening in the crop growing season, and it can cause strong damage to the crops. And basically, recently, the flash drought raised a lot of attention thanks to our folks doing satellite research, like Anderson, Atkins, and Chris Kine. They are able to use evaporative stress index to detect the flash drought. So like in the 2012, certainly a success case. But what is a flash drought anyway? Unfortunately, you talk to different people, you get different answers. The basic definition is a flash drought is a sudden onset of a high temperature and decrease of soil moisture. That everybody agrees. Now we have a type 1 event. And those satellite folks think about it is they say, okay, we have a heat wave. So the evaporation increases. So soil moisture decrease. But what precip? They do anything? Then if you're talking to folks doing Texas research, like experts like Ron Fu, Nelson Gannon, they are saying differently. They say, okay, we start from drought, a lack of rain. And then because the anticyclone sits here and seeing you enhance the dry condition and also increase the temperature, so you also end up with a heat wave. In that case, however, ET is decreases. So the question will be, if you don't have a precip deficit, will that be a heat wave? Okay, so because I only have very short time, I'm going to answer 3 questions for the flash drought. Okay, why do we have two types of drought? And also, do they have a preferred region to occur, or they can happen anywhere? What are the local physical mechanisms responsible for those events? Since the flash drought has a duration usually 3 to 8 weeks, so I use penta data rather than use monthly data. Surface temperature and the precip from University of Washington. These are precip and temperature analysis from station data. Unfortunately, we don't have observed soil moisture and ET, so I use 2 NLDAS, so not biased anything. One's NSTAP NOAA, another one is VIC. And the study period is from 1979 to 2011 for this talk. We're talking about growing season, so that would be April to September. Firstly, we wanted to see where do they located. We select the events. Okay, you want to have a high temperature, so the requirement for temperature is greater than 0.8 standard deviation. You wanted to drop off soil moisture, so soil moisture change has to be negative. After all, this is still a drought, so we require soil moisture also negative, anomaly also negative. Now, for the type 1 drought, we require ET positive. And for type 2 drought, we require ET negative. The 0.075 is arbitrary. We just need some small number. Okay, we will do NOAA and VIC separately and then take an average. And then we will show you the frequency of occurrence. Total penta versus the record, which will be 35 years. Okay, now you see the frequency of occurrence. For the type 1, it's really not that many events, only 40 to 50 events. They are in the eastern region basically, and also have a maxima in the north central part and Ohio Basin. Type 2 is much more events, and basically centered over Texas, but also in the Gulf State and the southern plains that extended to the Great Plains. So there are more events. It's about 10% of the total record. Interesting thing is in the places you have the maxima type 1, you still have type 2 drought. So type 1 is really a real occurrence. But since we don't know much, let's do a composite for all those events. So you see, you do have the raise of temperature. So, okay, that's satisfying the heat wave criteria. The positive ET, negative soil moisture total. So far, so good. The interesting surprise is that if you do the precip anomaly composite, you don't get anything. So, does P doing anything? Okay, let's look at the evolution. Basically, we composite the penta from -5 to 5 penta from the onset. The penta we identify as the drought. You will see signal starting -1. You have the temperature increased and then you decrease. It doesn't last very long. The maxima is only 3 pentats. There is a very good correlation between the increased temperature and the increase of the evaporation and the decrease of the soil moisture. Now look at the soil moisture. The drop of soil moisture starts onset and it lasts very long. So basically the damaging is from soil moisture, not that much from the surface temperature. That end very quickly. The interesting thing, did I say we don't see the precip composite? But in the -1 penta, we have very little, we still have some negative anomaly over the north central, and they also feed back to soil moisture. Is that a crucial element for the establishment of this type of drought? We will see later. Let's compare with the type 2 drought. You will see the soil moisture total has been constant almost over the 30-some day period because of previous lack of precipitation. Evaporation starts to change in the -1 penta, and also it's last to +1 penta. There's very good corresponding between the decrease of ET and increase of sensible heat. Of course, you have a high sensible heat, then you will have a high temperature. Again, you will see temperature heat wave does not last very long. Basically, it does damage again. It's really from the soil moisture. So if we don't have a precip, will we have a heat wave? To answer those questions, we did an experiment using the RIC model to isolate the influence of soil moisture by temperature and the precip forcing. Everything is the same as the control, the RIC stimulation we used, which was driven by observed precip and temperature surface wind. For the experiment, the same model, same initial condition, same T and windfall T. The only difference is now we take away the precip anomaly. We replace the daily observed precip to the daily climatology for the same record, and then see what's happened. So this way we'll isolate the contribution by temperature and the precip. Okay, now we compare the experiment with the control. All right, we still have a first type of fresh drought. They're about the same event. They are really close. We also see the increase of ET and also the increase of temperature. So they really is the type 1 drought. The only difference is soil moisture. If you have a control, that means you have the soil moisture, you have the precip deficit, then soil moisture depletion will be much more stronger. So you don't need to have a precip to initialize the event, but if you have lack of soil moisture in the beginning, then you will enhance the impact of those events. So why type 1 only happened there? Because you needed to raise the evaporation, and that means you needed to have the transpiration turn of evaporation, and that one depends on vegetation. So vegetation is really a critical element. If you have a high temperature, if you have vegetation, you have increased transpiration, you have increased ET, et cetera, up a chain of events. And that's why type 1 events only occur in the vegetation dense area and only occur during the growing season. And that's why the damaging is really tremendous. Now, what about type 2? That is precip driven, because for the experiment, we don't see any events far less than the control, which has about 100 to 120 of pentats. Okay, so, and also you have a very good correspondence between the happening of this event, a correlation between precip and the temperature in those areas. The correlation, as you can see, in the type 1 area, it's very small because you know the precip temperature has a different route. But certainly in the Great Plains, especially Texas, where the precip influence of temperature is high, you will have those type 2 events. Those are precip driven. If you don't have a precip anomaly, you will not have this type of events. Okay, the last question will be, does the meteorology drought over the type 2 area always have lead to heat waves? I took all the drought events. Those are meteorology drought events. Basically, you use SPI6 and you ask them below -0.8 D2 drought and persist for 6 months also. We take all those monthly means and composite the same months, the surface temperature. And you do see the positive anomalies. They are from 0.8 to 0.6. So if you have meteorology drought, basically you lack of precip. And then in the type 2 areas, you do have the raising of temperature because you have precip, so you lack of precip, your decrease of soil moisture, changes the Bovin ratio, and decrease the ET. So you have compensation of increase of sensible heat, and that's why the temperature increase. So now we try to conclude. But basically, this is really a fun project to study. We have 2 types of fresh droughts. The first part, which had not damaging, but basically in the vegetation dense areas, that's because the crop already start, or you just in the time to plant those vegetation, and then you have a very high temperature, and then you have this chain of the events, the increase of transpiration, decrease of soil moisture, the sudden dryness have a huge impact for the agriculture. It's not related to meteorology drought. You don't need a precip deficit to start this event. However, if you have a precip deficit, will enhance the impact because it will drive, already you have not much soil moisture, and this will driving you even lower. Type 2 event is very different. Basically, it's a precip-driven event. You need to have a precip, and you need, if you have lack of precip, that's start a chain of events, and that's what will have the flash drought, and that certainly you can detect with like SPI or any measurement for the meteorology drought. The implication of this is we really need to monitor it carefully, and we are so lucky to have ESI to help us. But the satellite record is not that long, so we still need an NLDS. Now, NLDS monitor doing the modeling ET. Each model have different way, and unfortunately, we do not have a lot of in situ data or flux towers to give ground truth to know how well we are doing, and this type of thing we really need to consider. But for the type 2 event, they happen pretty often because high temperature always will give, lack of precip will also give you high temperature, is whether it's high enough to qualify to be a heat wave or not, and that depends from events to events. I end up here, and I like to take questions. Thank you all.
Thanks a lot, Kinsey. That was great. So for those who are attending virtually, please send questions for Kinsey to me using the chat feature. I haven't received anything yet, so in the meantime, I'll see if there are any questions here in the room. Anarita?
Yeah. Hi, Kinsey. This is Anarita. Very interesting, very thought-provoking. And I have, I guess, a two-part question. So does your conclusion speak to the predictability of these two types of events, different type of predictability? And the second part of the question is, based on your categories, if you like, are we able to tell when we are in one, when basically a drought is initiated, are we able to tell which type of drought, flash drought we are in? And so, again, whether we have a higher likelihood to be able to predict one type of drought or the other.
Yeah, I did look at some ones, even though I'm not giving here, is that for the type 2 drought, it is not that difficult because, you can, for the monitoring part, you can just look at the SPI index because if you have, it will detect ordinary drought or meteorology drought you want. And since we are heavily monitor the soil moisture and all those, and the temperature will raise, so just watch temperature, which also is something we can monitor. Type 1 is entirely different. Because, and also, the predictability. Type 2, most model is able to, to capture the physical mechanism from lack of precip to raise of temperature. Some of Matty Hurley and Richard Seeger's work seems to all point to that. So this type of drought is kind of more quote-unquote friendly to prediction. Type 1 is very difficult because it's only lasts for 3 to 8 weeks. It's not very long. To monitoring, I think we need to really look at the ET more carefully. Then if your ET is positive, you have very high temperature and the soil moisture drop, then you have those events. But it is a little bit difficult to predict because in the same area, as you can see, both type 1, type 2 can happen. So they are competing with each other in a sense because you're already in the drought. So type 1 is a little bit more difficult to predict, and it is you wanted to predict the ET and the precip rather than ET and soil moisture rather than precip because you don't really need a precip to initialize this event. Many people say I can use SPI to predict the type 1. Well, I guess probably not a good idea because they are not really that much related.
Okay, thanks for the question, Maria. I haven't received any other questions through the chat feature, so thanks a lot, Kinsey, for the presentation.
You're welcome.
So we'll move on to the next speaker, which is Scott Weaver. Scott, are you on the line?
I'm here.
Great. I'm going to transfer control over to your computer. And then just click the Share My Desktop button. So for those who joined after the intro, we're going to hear from Scott Weaver next from Climate Prediction Center, and then he'll be followed by Gabe Vecchi, and then finally by Chris Thorncroft from SUNY Albany. So Scott, it looks good. So whenever you're ready, go ahead.
Okay, great. Thanks, and thanks, Kingsley, for your interesting talk about drought. Today, I'd like to talk to you a little bit about North American low-level jet activity and its influence on seasonal tornado variability. And this is work that I've done in collaboration with a few people here from the Climate Prediction Center. Stephen Baxter, Emily Riddle, and Arun Kumar had various input into this research, this diagnostics that we're looking at. Well, first, I just like to take a step back and give you sort of a global view. I like to show this figure because, you know, some people think that in North America we're sort of alone in the low-level jet universe, but when you really look at it in terms of the global circulation, you could see that low-level jet activity is a ubiquitous feature of the large-scale climate and the circulation, usually appearing in the warm hemisphere. So I always like to show this figure to give you kind of an overview that their presence is really felt on nearly all the continents of the world. But closer to home, in terms of its relationship to North America, you know, today I'm going to talk a little bit about severe weather, but I also wanted to clue you in as we funnel down into North America that there are other impacts that low-level jet variability has. It's a very interesting phenomenon. It's responsible for periods of drought and floods, which Kingsley just spoke about, flash droughts. And if you move from the upper left and go clockwise, this picture here is the Iowa floods of 2008, the pigs on the roof. I always love to show this picture because I think it's a really interesting statement. If you move clockwise, you could see here there's some indication that Great Plains low-level jet variability is influential over the observed warming hole in the central United States, which goes somewhat against the global warming predictions, why we have warming around most of the continent, but this temperature hole in the middle of the U.S. Recently, also, I became aware of a paper that related Great Plains low-level jet variability to the populations of jellyfish in the Gulf of Mexico, so I thought that was kind of neat. But today, I'm going to focus in down here on severe weather, and we're going to use tornadoes as kind of our comparison and our target. So let's talk a little bit about some climatology and seasonal cycle for those of you who may not be as acclimated to this phenomena. So here you're looking at, in the upper panel, you're looking at the mean 850 millibar meridional wind. This is taken over 1950 to 2010. From the NCEP NCAR reanalysis. This is the April to September mean wind, and you could see the classic Great Plains low-level jet signature in the mean wind. Now, I typically been calling this a North American low-level jet because when we speak about variability, I'll show you structures that go outside of the Great Plains. So it's really, I think, more apt to refer to it more in the North American context. Looking down below here, we see the seasonal cycle of the meridional wind averaged over the eastern two-thirds of the U.S. And you could see, even when you go outside the Great Plains, you do have, you know, include other portions of the U.S., you do have, you know, a maximum that reaches in June and then starts to decay through the fall and into the winter. And if you were to plot the tornado occurrences, you also get a similar looking graph, although there's a much more precipitous decline through midsummer. So just to give you a little background. Now, talking tornadoes. When we talk about tornadoes, first I have to give you a caveat, and given the interest in keeping short here, there are many problems with this tornado database that we could probably talk about an hour on. So what I'm doing here is I'm including all the tornado counts. There are some biases with regard to the early versus the later record, but just in terms of the climatology here, I'm talking about all the tornado counts. That includes the F0 to F5s. And when you break it up by region, you can see that their climatologies have distinct peaks. So in the southeast, for instance, the green line, you get a double peak in April and May, not as strong as the other regions. So in the southern Great Plains, you have your peak in May, and in the northern Great Plains, it's in June. So your seasonal cycle actually moves clockwise from the southeast through the southern Great Plains and into the northern Great Plains. If you were to form a standard, climate anomaly index like we do with precipitation or any other quantity, and look at it on a regional basis, this is what you would get. So you're subtracting the climatology from each year's value. And I just wanted to show this to give you some sense for the variability in the tornado counts. You can see in the 50s there's a sort of a tornado, what we call tornado holes. You could see the big outbreak in 1974, the big season in 1973, and that's a whole nother topic, how you can have two similarly looking years, but they really emanate from a very different climate context, one having one or two major outbreaks, another one being sort of increased activity throughout the entire season. You see this other really interesting feature in the mid and late 80s where you had a dearth of tornado activity, and then in the recent times it seemed to pick up, or so we think. This pickup is very dependent on the strength, but again, as I mentioned, for this talk I'm using the full range of tornado counts. So let's talk a little bit about North American low-level jet variability. Here what I have plotted for you on the left is North American low-level jet variability modes and their precipitation regressions. So you form the regressions by basically taking the principal component time series from the EOF analysis and look at the most likely anomaly pattern you get. And when you take this over the 61-year period and you look at the first two modes, you basically get in mode 1 a very enhanced southerly meridional flow. You could think of this as fluxing heat and moisture northward, having divergence in the entrance region and low-level convergence in the exit region, and widespread precipitation throughout the Great Plains and the upper Midwest. For mode 2, you have somewhat of an eastward shift, and right along this line here, this convergence line, and into the southeast, you get enhanced precipitation. What's really interesting, I also wanted to show you that if you break this up by an early and late period, you could see that the core of the variability modes is actually beginning to shift when you look at it in terms of the more recent period versus the earlier period, and both modes exhibit this behavior. You also notice that there's somewhat of a stronger precipitation footprint for mode 1 and to some extent mode 2 in the more recent period. That's just a little interesting nugget there, because some other people are looking at how variability is intensifying with regard to the upper level storm tracks in the most recent period, and so we thought we would take a quick look and see if the low-level jets were being similarly influenced. Getting back to the 60-year record, if you look just like we did at the tornado time series, if you look at the time series for the North American low-level jet modes, you'll see that mode 1 it really does show, you can really see in the midst of the interannular variability, you really can see some decadal-like feature where it was much stronger positively. So you could think of this as more of an enhanced precipitation mode in the earlier period than it has been in the more recent period. With regard to the tornado situation, here you have principal component, or mode 1, was very strong in 1973 and 1974, and in the mid to late 80s was very weak. So you could think of this as the mid to late 80s situation as a very weakened low-level jet activity. Similarly, for principal component 2, you also had weakened activity. So it's kind of interesting because both of these modes were very weak when you had very weakened tornadic activity over both the Great Plains and the Southeast. So looking at these in terms of just correlating the two time series, we were curious again to just see how are they correlated as a function of region. I mean, the low-level jet modes themselves, they don't lend themselves to just nicely being in the southern Great Plains or northern Great Plains or southeast, but in general you can see that mode 1 is active a little bit more over the Great Plains and mode 2 shifts a little bit more to the east. And so what is that relationship like? When you look at the correlation across the 60 years in the northern Great Plains, it's low, but quote, statistically significant. If you look at it as a function of period, there's actually been a slight decrease in the correlation over the northern Great Plains. Not a huge decrease, but we wonder, is that because of that shift southward in Mode 1? Interestingly, looking at the southern plains, the correlation is nearly doubled when you go from the early period to the recent period. And again, we're thinking that that's related to that southward shift and the dynamics that are going with it to promote the environment for tornadic activity. In terms of Mode 2, no surprise that it has a little more influence over the southeast than over the Great Plains. So that's just the basic take-home message there. What's really interesting, if you do a back-of-the-envelope calculation and just, instead of looking at correlation coefficients, just think of this as, okay, count up the times when PC1 and PC2 are both positive. So essentially the way you can look at that is both of these situations are occurring within a season. You basically have really strong enhanced southerly meridional flow, you have enhanced precipitation, much of it convective in nature, and you have the dynamics that go along with that situation. When you have both of those positive, how many times will at least one region have above average tornadic activity? That occurs 14 out of the 18 times. But if you look at all regions, it's only 22% of the time. So it's not necessarily, even though you have all that flow encompassing 2/3 of the eastern U.S., you don't necessarily have a definite indicator of enhanced tornadic activity. On the other hand, when they're both negative and you're looking for below average activity or negative anomalies in tornadic activity, at least one region, 100% of the time in the record, had below average activity, and all regions 69% of the time. So this tells us that when you just look at this sort of qualitatively, that this is probably a better indicator of tornado seasons that are weaker than those that are stronger. And that somewhat makes sense to me, because the situation you need to produce tornadoes is so specialized that I think it's easier to not produce them or to have weaker years. The dynamics that favor that situation are they govern the situation much better than when you have the promotion of the dynamics. If you're wondering how, we've only looked at precipitation regressions. If you're wondering how do the modes do this, what are they actually doing in terms of setting up the tornadic environment? Here we're looking now, instead of the NCEP NCAR reanalysis, we're looking more in the recent time period at the climate forecast system reanalysis, and we've selected two tornadic parameters, or what are thought of as being conducive to tornadic environments. One in blue being the 1,000 to 500 millibar meridional wind shear, and the other one being low-level helicity. Both of these are indicators of shear or spin in the atmosphere, and you could see Mode 1 is really influential on the lower atmospheric shear. Mode 2 not as much, but the helicity is a little bit more important in Mode 2. And the reason why we plotted these two is, I'm not a mesoscale guy, but there's some debate over, at least there was some years ago, over what is really the more important parameter here. And I'll leave that to those gentlemen and ladies to figure out. Now looking in terms of prediction, we're interested in how well is our models, our climate models, depicting these modes, since they seem to be important for severe weather activity. So what you're seeing here is we've recalculated the modes in the climate forecast system reanalysis for 1983 to 2013, so it's a little bit of a different time period. We did that because we need to coincide with the hindcasts from the climate forecast system version 2, so that everything's over the same time period. The precipitation you're looking at here is observed precipitation. And down here you have the ensemble average of the 172 runs prior to April, May, and June that are available in the hindcast. This is just to kind of get a feel for, does the CFS version 2 even produce these modes, and how well do they produce the relationship between these modes and precipitation, since that's also an important diagnostic here, as these modes are important for drought and flooding events as well. So we're also looking at this in a larger picture. And you could see that they generally capture the structure of the modes and the relationship to precipitation, so we could say this is planet Earth. Looking more closely at how well each run is doing, see, that was an ensemble average. What you can do is you could take the pattern correlation between what the model thinks is its Mode 1 or Mode 2 and project it onto the observed patterns and see what your pattern correlation is. And if you look across the 172 runs, you'll notice that Mode 1 is the correlations are not as high as in mode 2. In other words, there are some runs that come out where the spatial structure is not quite on target, but all in all, pretty high correlations. Mode 2 is much better. More of the runs have a much higher correlation. So again, this is just a way to look at how the model simulates these very important modes of regional climate variability. In terms of skill, we just started looking at this. So here we have plotted, this is basically just 2 time series. It's the CFSR in blue, so that's your target. That's your historical time series. And the CFS version 2 in red. This is the 20-member forecast for April, May, and June for mode 1. So we're pretty close to the target time frame. These are all from March, which is sort of our first cut. We want to see how well it's doing, and overall over the time series, not too great, although not really unexpected. You're trying to forecast meridional wind anomalies, essentially preferred patterns of meridional wind anomalies over the entire spring season. What I will say that's interesting is there are some times, and more in the recent period, where the correlation seems to be higher, but it's unknown whether that's some type of decadal variability influence on the skill or if it's just pure chance. One really concerning thing to me, though, I'd like to point this out, is so this is mode 1. So here in 1988, you could see mode 1 was very, very weak, or excuse me, very negative, which means nearly the absence of a Great Plains low-level jet, and you could think very weak moisture fluxes onto the continental U.S. But the CFS version 2 thought we were going to have essentially what would be equivalent to something like the 1993 flood. So, there's definitely limitations here, obviously, so need to point that out. Mode 2 forecasted a little bit better, and so, the correlation coefficient's a little bit higher here at 0.41, and again, there are successes and failures in terms of how they're doing. So now we're going to start looking at, when we have skill, why is that? Why might there be differences in skill? And so this has just kind of started this aspect of the analysis. But it's I just want to drive home the point that it's not just severe weather, but it's other activities that are important, and especially as NOAA moves forward with goals regarding regional climate variability and change, we think this figures prominently in that area. So that's it, and I'm happy to take any questions.
Great, thanks a lot, Scott, for that interesting overview of what you've been working on. Any questions here in the room? I don't have any chat messages yet, so any questions from anyone in the room?
Scott, this is Rick Rosen. It's been many years since I read Fawbush and Miller, and the criteria, kind of patterns that yield best chances for tornado outbreaks. Would an analogous approach or a different approach have been, or do you think it would be productive to look at those kinds of synoptic situations? I know you were focusing on the low-level jet, but those kinds of synoptic patterns that give rise to tornado events, and see what the change has been in those kinds of patterns over the last couple of decades? Is this making
Yeah, of course. I mean, there's one thing, the thing that's interesting here, or the thing I guess you could say that might be a little bit lacking, is there are different ways. If you're going to connect it to the low-level jet, there are different ways to get low-level jet variability. So, and what I mean by that, so for instance, you could have low-level, say in some years the Bermuda high is a little bit stronger than it normally is. That's usually associated with a stronger low-level jet. In other years, you could have your storm track come a little bit further south. That can similarly influence it. So, yeah, your comment about looking at this, in terms of synoptic environments, sure, I think that's worthy. This is just another way to look at that. I mean, these low-level jets, I mean, traditionally, the first research on them was more of in a synoptic type, analysis. But, as time moved on and we had access to better climate data, things have shifted into the climate arena a little bit. So, yeah, absolutely.
So I do have one question, Scott, from David Rockwell, who's on the line. David, are you there?
Yeah, yes, I can hear you.
Yeah, okay, go ahead and ask your question.
I was wondering if you have an estimate of the forecasting skill for the National Weather Service in predicting tornadoes.
On what time scale? I do not on the climate time scale, because as of right now, there's no operational, seasonal or even 2-3 week prediction for tornadic activity. Although there are some indications that something along those lines may be possible within the next few years, but right now it's somewhat tenuous.
Okay, thank you.
Sorry about that.
Okay, thanks for the questions, and I think we need to move on. So Scott, thanks so much for the presentation.
Thank you.
Okay, Gabe is the next speaker. Gabe, are you on the line?
Can you hear me?
Yes.
Perfect.
Okay, I just transferred control over to your computer. So share your desktop and then take it away.
Oh, yeesh.
This is the hard stuff.
Share desktop. View. Full screen mode.
Perfect,
right.
Yeah, go ahead.
So today I'm going to talk a little bit about a new prediction system that has been developed at GFDL recently. This is work that has, I'm just a mouthpiece. This is a large group of people in NOAA's NOAA GFDL's Climate Variations and Predictability group that are behind this. And this piece of work has sort of, it aims to create a prediction system, but the prediction system has sort of two goals. It has one, a scientific goal to serve as a framework by which we can test some hypotheses underlying the prediction methodology. And then it also has a much more practical goal in order to provide sort of information about the future. And the hypothesis essentially that we're testing is that enhanced resolution in the atmosphere and land and also correcting the large-scale biases in the model will lead to better predictions of regional climate and extremes. And of course, the climate goal, the practical goal is to predict those regional climates and extremes. Now, we're building here at GFDL on a history of success in seasonal hurricane prediction. This is a plot that if you haven't seen it yet, you've been missing out. This is by some work by Jen Hui Chen and S.J. Lin, and they show what is, to me, a very remarkable retrospective skill at predicting North Atlantic hurricane frequency, with the black line being the observed hurricane frequency over the past, up to then, the past 20 years, and the red line being the forecast from a 25-kilometer model initialized on the 1st of July. The retrospective correlation approaches 0.9, and it's really amazing. Now, we at GFDL, we have also built a hybrid statistical dynamical forecast system, building on a lot of work that we've done prior to that to try and understand the response of hurricanes to decadal to centennial perturbations. And in the hybrid statistical dynamical system allowed us to go back to predictions starting in October of the year before and displayed retrospective skill at basin-wide hurricane frequency. And we've been updating that data online. You can go to this website and see how our updates have gone, sort of as a way to evaluate the prediction system in real time. All published forecast systems, I think, will have retrospective skill, or else they won't get published. And so what we want to do is evaluate it after we've published the methodology to make sure that that forecast skill stays. Now, one of the questions that we've been wanting to move towards is, rather than focusing on basin-wide frequency, which is a target that many people have been aiming for and succeeded at hitting, we wanted to try and get to more regional information. And the reason we wanted to get to more regional information, I think, can be illustrated here. If you look in the left panel, there's a bar chart, the furthest left, showing in all the little colored symbols are predictions that were made prior to the 2010 season by different groups. The red bar happens to be ours, but there's a whole lot of prediction systems there. And they all successfully predicted that 2010 was going to be, in a basin-wide sense, very active in the Atlantic. However, that correct prediction for basin-wide activity in the Atlantic would not have given you the sense that none of the hurricanes hit the U.S. in the Atlantic ahead of time. And so in order to make decisions based on the prediction information, you want to have much more regional information. So the question we want to ask is there a way to reliably predict statistics of storms beyond basin-wide? Can we provide much more regional information, and which would, in our opinion, be much more practically useful? Now, a vehicle to do that, we think, would be to go to a high-resolution couple model. Our seasonal predictions up to last year, or March of this year, had been done with a relatively coarse resolution model, or 200 kilometers in the atmosphere, although we'd had a lot of experience at the laboratory over the past 5 or 6 years through an effort led by Tom Delworth and Tony Rosati at building coupled high-resolution models. And these models were yielding much better simulation of large-scale climate. For example, here is, and also regional climate. Here in the leftmost panel is the monsoon rainfall from our low-resolution model, CM 2.1, a model that was judged by a variety of papers to have one of the best, if not the best, monsoon simulation in the CMIP3 archive. And the CM 2.5, which is our new high-resolution model, a quarter-degree ocean and a 50-kilometer atmosphere, has a much more faithful representation of the monsoon, as you can see here, comparing it on the further right to the observed. Now, it wasn't just the monsoon that got better. This is a multi-model assessment led by Reto Canuti, where he and his co-authors try and assess how similar models are to the observed climatology of surface temperature and precipitation. And the bars here are, each one is a different model from the CMIP5 archive. And the length of the bar is inversely proportional to how well you match observations. So a shorter bar matches observed climatology best. And what you can see is CM 2.1, our old model, landed somewhere around where this vertical line is. And CM 2.5, which is the second bar from the top, was a considerable improvement from CM 2.1. So changing resolution led to improvements in global climate simulation. And what we wanted to see is, can we harness these improvements? Can we harness this high resolution to give us improved prediction? Of course, CM 2.5, the whole development of CM 2.5, and all the work that I'm about to show following on for CM 2.5 was made possible because of enhanced computing. So computing was a necessary factor in order to achieve this, although I think having the long lead development here at GFDL, having all these models ready to go really was also a necessary factor. So CM 2.5 is a high-resolution model both in the atmosphere and in the ocean. And since our goal had been to focus on extremes in regional climate over land, we asked ourselves if there was a way to sacrifice resolution in the ocean in order to maintain resolution in the atmosphere and land and still be able to do a whole lot of experiments, because the ocean costs a lot to do, the atmosphere costs a lot to do. If we do them both, we can do fewer experiments. If we only do one at high resolution, then we can do more experiments. We have settled on what we end up calling GFDL FLOR, which stands for Forecast-Oriented Low Ocean Resolution version of CM 2.5, or FLOR is flower. That's much nicer than that long word. And it is a model which has a 50-kilometer atmosphere, but it has a 1-degree ocean. So it's essentially CM 2.1's ocean and CM 2.5's atmosphere. And with it, we're able to get about 15 years a day running on the computer, and we can do large ensembles and do retrospective predictions. Now, the hypothesis underlying FLOR is that enhanced atmospheric and land resolution improves our simulation of climate. And here is a way to illustrate this, a series of annual mean plots on the left of precipitation, on the right of annual surface temperature. The precipitation is then compared, the observed on the top, the high-resolution model in the middle, and the medium resolution CM 2.1 on the bottom. And if you really squint, they all look the same. But if you start looking at regional details, you will see that there is considerable improvement with the high-resolution model and the improved land model. In particular, rainfall over the Amazon increases and matches observations better in FLOR. And then also this dry line across the center of the U.S., separating east and west Texas into the north of it, is better represented. And there are also improvements in the precipitation. Also, now that I'm looking at Stauffer here, he reminded me about this. The ratio of Congo to Amazon rainfall is much better represented in this model. It's something that we hadn't seen prior in many models, or any. And so this is an incredibly exciting development coming from resolution. And now the focus of this talk is going to be tropical storms. And this model, we've been using it both to do predictions. It has tropical storms that emerge at 50 kilometers. The intensity isn't as strong as in observations because of the low resolution in part. But they happen in those similar places as observed, and they have similar tracks as observed. And then we can also use this same model to explore the response of hurricanes to greenhouse gases. We can use it to explore the response of hurricanes to volcanic forcing, all sorts of different forcings. And here's an example on the bottom of using this type of model to look at the response of hurricanes to CO2. So essentially, it's approaching a seamless seasonal to centennial prediction effort. Now, the FLOR results in a improved prediction of basin-wide hurricane activity relative both to our old seasonal forecast system, the one that used CM 2.1, as well as many others that are out there in the literature. Shown here, this is just a scatter plot of the retrospective correlation of two versions of our model. The vertical axis is the retrospective correlation in our model. The horizontal axis is the retrospective correlation in other previously published methods. The maroon symbols is the ECMWF. The red symbols are Klotzbach and Gray, Ming Zhao's work, Tim LaRose, Hui Wang's, and Chen and Lin's. And what you can see is, by and large, the symbols are above the diagonal. And the one model that beats us consistently is this purple symbol, which was that initial one I showed you of Chen and Lin, that 25-kilometer HIRAM model here at GFDL. But at long leads, the model does very well, competitive with other prediction systems. Now, the goal here, and what I started out talking about, was not basin-wide activity. The goal is, can we reliably predict statistics of storms more regionally than basin-wide? And here is an effort to suggest that we may be able to do this. Instead of looking at basin-wide frequency, what we do is we look at the tropical storm density in a 10 by 10 degree box. So centered at each 1 degree point, you center a 10 by 10 degree box, you count how many tropical storm days there are in it, and that's your density of tropical storm in that season. And then you compare the predicted density with the observed density. These are seasonal predictions, initialized July and run for the rest of the year. And wherever there's colored shading here, there's a statistically significant at p equals 0.1, p less than 0.1 rank correlation of the predicted and the observed storms. And what you can see is that over a broad area in the tropics, at least in the Pacific and the Atlantic, there is significant retrospective correlation between observed and predicted, initialized on July 1st, tropical storm density. And we've looked at this not just for July starts, but we look at it for other starts, and we find that we are able to extract broad areas of significant retrospective correlation going back as early as January of the year before. This suggests that this type of target, regional tropical storm activity, may be a feasible target to make. So what does one of these forecasts look like? Well, this is here, a real forecast. This was initialized on April 1st of this month. This is from a model that was sent to the North American Multi-Model Ensemble. So FLOR has been contributing to the North American Multi-Model Ensemble since March. And shown here are the predictions initialized 1 April 2014 for the anomalous tropical storm density over the coming year. Red colors indicate increased density, blue colors indicate decreased density, and the contours show all the density anomalies that are predicted, so dashed means fewer. And but the shading is where the predictions initialized on on April 1st from 1980 to 2012 had a retrospective significant correlation. So places where we might hope to believe the forecast. And what you can see is, in large part reflecting this model's prediction for a strong El Nino, is an increase in density in the tropical Pacific and a decrease in density in the tropical Atlantic. Now, we don't have the verification for this yet, but it's, you know, we can make this forecast. It's kind of exciting. So in summary, I think increases in atmospheric resolution, land resolution, and I should mention as well, improvements in the representation of land processes yield both improvements in large-scale climate simulation and prediction, as well as enable the prediction of regional climate and extremes. I didn't show this, but there's a paper by Li Wei Jia submitted to JClimate, showing that predictions of regional precipitation and temperature are improved in FLOR relative to CM 2.1. It appears that on seasonal timescales, predictions of regional tropical cyclone activity may be feasible, although you need to run a large ensemble size to actually, you know, beat down the noise. Something I didn't discuss very much here, but is an interesting result, is that correcting systematic errors in the model, correcting systematic large-scale errors in the model leads to improve simulation and prediction of large regional climate and extremes. This is a number, flux adjustment adds about a season to the lead of our tropical storm predictions. And keep your eye out. We're going to have a whole lot of papers coming out in the months ahead on FLOR results. And if you go to this website over here, you can download the submitted versions of our two first FLOR papers. Thank you.
Yeah, we're all very excited about all these FLOR papers coming out. So any questions for Gabe? I queued up on the chat. I haven't gotten any questions via that feature yet, but here in the room, any questions for Gabe?
Yeah, Gabe, this is Anarita. Yeah, very exciting stuff, definitely. I guess I want to throw you a question. I mean, do you have a sense why, you know, you can sacrifice some resolution in the ocean and still get you know, good results? And I guess the second part of this question would be, if you had, you know, additional computing resources today, would you throw them in the atmosphere? I mean, higher resolution in the atmosphere, or would you throw it in the ocean?
So that's an interesting question. So why can we get away with not as much resolution in the ocean? I think it's because of the quantities we're focusing on here. We're focusing on land, atmospheric extremes, and so those are most connected to the atmosphere. Also, I think one of the issues with the ocean resolutions that we've been exploring, a 1/10 degree and a 1/4 degree, is that the parameterizations in the ocean for oceans of that resolution are not as mature as for the 1 degree resolution that we've been running for now, I don't know, decades, is it? And so you know, it's been that the, you know, there's a lot of factors that are at play. I think, I don't just think this, I know this, that if we were looking at the deeper ocean, there would be a great benefit to going to a 1/10 degree ocean as opposed to this 1 degree ocean. But you know, that you have to make sacrifices and compromises as you're doing this, and this was very goal focused. Now, where would I put additional resources? I have a long list of ways that I could spend additional computing resources. I think everybody in this room that I'm sitting in here right now, or standing here right now, has their list as well. So I think that for some problems, I think additional oceanic resolution would be very important. I wouldn't mind making this atmosphere have a higher top, better resolved stratosphere. There's some indications that that helps with the predictions of the NAO. I also wouldn't mind adding some comprehensiveness to the atmosphere. Right now, there's the atmosphere that we're using has relatively simplified representations of many processes, and so I wouldn't mind spending some resources there. And then, of course, I would always love to spend more resources and more ensembles. So there's, and keep going. I mean, this is a Christmas list. I'll keep making it bigger and bigger.
Sorry, no, wrong question, I guess.
Okay, I haven't gotten any.
I'll tell you that, you know, for any of those things, there's practical benefits. You know, they're not really hard to show. And you know, something I should mention here is that this FLOR project, it took us about 18 months to go from conceiving the model as an idea to delivering our first pseudo-operational forecast to the NMME. And that was made possible only because we had the GFDL research and model development that had gone on for years before that, so we could tap into that immediately. And then we also had access to the fast supercomputing. And so there is a very clear demonstration that this long lead research and these computing capabilities yield very practical results.
That's well said, yeah. Okay, I haven't received any chat questions. Any other questions here in the room?
I have a quick one, Gabe, but that was very interesting. On your results that involve the 10 degree by 10 degree box, I gather, or I speculate that the skill you were showing in the Gulf states for landfalls was probably because you were capturing storms that were forming in the Gulf, and as opposed to ones that came off of Africa and recurved, where you also have some skill. So it would be interesting. I presume you've looked into that, but I assume that might be the case.
So Rick, yeah, there is part of this is a manifestation of just predicting basin-wide activity, and that reflects onto regional activity just naturally. But part of it does come from distinguishing years when you tend to have more recurvers and years that you tend to have more straight shooting storms. And so as a parallel effort to our dynamical modeling here, as a way to understand the model and maybe improve on the dynamical modeling, we have a statistical modeling effort to try and do some nonlinear statistics on storms, to do some cluster analysis, to really try and extract more information out of these models and also more understanding out of these models than just looking at the model output itself would give us.
Thank you, Gabe. You opened the door for one short additional question from me. The year 2010 notwithstanding, is it true that years that have more basin-wide storms typically have more U.S. landfalling ones?
There is a statistical correlation in the long-term sense between basin-wide activity and landfall, but one of the main factors driving variations in landfall of hurricanes in the U.S. is the fraction of storms making landfall. So we have Gabriele Villarini, Jim Smith, and I have a paper describing this. If you look at the records going back to 1880, one of the dominant sources of variability is fraction of storms making landfall, not basin-wide activity.
Okay, thanks, Rick, for the questions, and thanks, Gabe, for the presentation. Okay, we're going to move on to final speaker, Chris Thorncroft. Chris, are you on the line?
Just undid my mute. I'm here.
Yeah, hi, we can hear you now. So just share your desktop so that we can see your screen.
How's that?
Yeah, and go full. Yeah, okay, go ahead.
Okay. So this is now moving into the noise, as Gabe referred to it. So I'm talking about more weather and weather variability on synoptic and intraseasonal timescale. So the type of activity that can affect tropical cyclones within a season. And a lot of my work has been emphasizing the role of easterly waves and the role of Africa in affecting that variability. So I'm going to give you a brief background on easterly waves and the West African monsoon, and then I'm going to talk about two things. One is the variability of wave structures and the relationship to tropical cyclones. It's been my long-term ambition to be able to look at an African easterly wave leaving the African coast and say whether that was a good wave or not in terms of developing into a tropical cyclone. So that's looking at the weather. And then I'll have a brief few slides talking about intraseasonal variability of wave activity. So why do waves come in bursts or not, and how that relates to tropical cyclones. Finish with a summary and maybe a new tool for monitoring easterly wave structures during a season. And the figure below, actually, on this slide highlights how convection is organized on synoptic timescales. This is kind of easterly wavelength coming across the African continent. Background here in terms of the West African region. the dominant climate features are the African heat low, hot to the north in the Sahara Desert, and a cold tongue that develops during the spring and into the summer, helps to drive a monsoon circulation, giving you rainfall over the continent. The yellow is the Saharan air layer, which sometimes has a role to play in tropical cyclogenesis or determining or influencing that. African easterly jet exists at around 700 millibars and is present there in association with this temperature contrast between the land and the ocean. Now this jet somewhat supports the growth of synoptic scale easterly waves moving between Africa and the ocean. What's very interesting about these waves, they interact with convection, mesoscale convective systems over the land, leading to growth of these systems. And as I say, easterly waves are often the most common precursor for tropical cyclones, especially in the main development region here in the Atlantic. Just to highlight the passage of waves between Africa and the Caribbean and North America, these are just four storms, that affected U.S. and the Caribbean during 2005, and these are just snapshots of the convective signal as they moved across. So all of these systems started their life over Africa and became storms over, and this is Ivan over the Yucatan, highlighting the link between Africa and the Western Atlantic. So in terms of observations and analyses, what does an easterly wave look like? This is based on basically a composite regression or similar to a composite, highlighting the synoptic. This is stream function at 850 millibars, has a wavelength at around 3,000 kilometers. This is the trough at 850 millibars, has convection within the trough. In the ridge, there's suppression of convection. So blue here is the enhanced minimum in OLR, with convection at the west coast and suppression behind. And I'll be very much focused on the structures of the waves at this coastal region because of their influence on tropical cyclogenesis. So this is actually day 0 in this regression analysis. I can take it back just so you get a flavor of the evolution of the waves to 4 days prior. So 4 days prior to easterly waves arriving in this coastal region. The first indication is often some convection. This is in the Darfur region, actually. Sometimes you can trace it back further east. So in terms of this regression, the first signal is this Darfur convection. So if you can keep your eye on that, you can follow this system as it goes forward. As it moves across, you tend to have convection ahead of this trough, moving towards the date line. This is 1 day prior to the coast, and convection starts to move in towards the trough a little bit more, but still mainly in the northerlies. And then we have convection within the trough at the coast. And I'm going to highlight this region in particular as we move forward. This was some results of some work I did a long time ago, actually highlighting the storm tracks, easterly wave storm tracks. And these are storm track statistics for the vorticity associated with the waves. This is 700 millibar vorticity track. And you can see there's a weak track over the land that develops as you move between the coast, between the land and the ocean. So this is the one that heads into the MDR. Over the land, it's interesting. You tend to have 2 tracks. One is to the north that grows on the surface baroclinic zone, just south of the heat low. And we have another one that develops at the coast. So easterly waves tend to track along the jet and develop significant low-level amplitudes at the coast in this so-called Guinea Highlands region. And that is a region that I've given a lot of emphasis to in terms of understanding variability in easterly wave structures, because obviously this is the precursors for tropical cyclones. And having low-level vorticity in particular is obviously a good characteristic of a wave for determining genesis or not. And just as background highlighting this region, this is the mean rainfall for this West African region, and there's some not insignificant but not huge topography in this region, coinciding with land sea breezes, etc. It leads to this rainfall peak, climatological rainfall peak at the coast. So my hypothesis is that easterly waves come through here and they actually get invigorated as they pass this climatologically active rainfall zone, and especially at low levels. And so my hypothesis has been that if easterly waves develop these structures at low levels, that they may become more favorable for genesis. And this was looked at in a study a few years ago. These are vertical cross-sections of relative vorticity at the coast at this longitude here. Again, so these are height longitude sections. And this is the typical structure. This is the mean for this period. These are developing tropical cyclones. We have 33 numbers here. So we have significant vorticity, 850 millibars. Down here we have vertical motion in contours and relative humidity shaded. So these are moist seedlings, if you like, with significant low-level vorticity. And if you look at the non-developing, of which there are many more, of course, the vorticity is weaker, some indication of drier air out ahead and even in the vicinity of the wave. But this number is very large, 512 compared to 33. And actually, if you take the 33 most intense non-developing waves, you end up having a wave structure that looks actually more attractive, if you like, in terms of vorticity than the ones that do develop. So that's led us to try and explore the variability in favorable systems. So it might be easy. I mean, there are very many weak systems coming off the coast that are kind of easy to determine whether they're going to be tropical cyclones or not. But what is it about these very strong, favorable-looking systems? Why don't they develop? And so this is some study with a recent occurrence student that highlights developers versus non-developers. And in this case, the non-developers are chosen to be very favorable systems. So by very favorable systems, we mean they have large vorticity, there's a lot of convection associated with them. And this is the composite of, I think it's 55 waves of developers and 55 waves of favorable developers. So looking at day 0, this is the relative vorticity, 850 millibars, and you can't tell much. They're very similar, I would say. And you can trace them back to the day before, 2 days before, and there isn't a lot of difference between these structures as they arrive at the coast. So why don't these non-developers develop? And so we composited other fields, and the signal that came out strongest was this one. This is just the day 0 structure reshown with this vorticity leaving the coast. So the most important difference between developing and non-developing, given favorable structures at the coast, actually turns out to be low-level relative humidity ahead of the system. So this is the location of the trough for the developing systems leaving the coast with storm relative flow included in streamlines. And this is the location of a moist anomaly compared to climatology. So the ones that develop have a moist anomaly ahead and pretty close to the system, whereas the non-developing systems, which are equally favorable leaving the coast, have a weaker anomaly or even dry anomalies out ahead, and with a suggestion that the difference between the developing and non-developing is often associated with this moist low-level air getting into the developing systems, whereas dry air is getting into the non-developing systems at low levels. Just to highlight this in terms of real cases, this is the Dean. This is the vorticity structure leaving the coast in purple contours here, very moist. This is the downstream moist wave, and as you can see 2 days later, they're actually quite close. The wave ahead actually tends to stall. Moist air is getting underneath this system, and this formed a few days later. The next wave coming off the coast did not develop, and that's this one here. This is Nadine. But what's different about these two cases is a more pronounced ridge with dry air out ahead. And even 2 days later, you can see some of this drier air is getting in. So the shaded here is total precipitable water. So dry air is actually getting into this system. And you can see this is like a time series, if you like, of the rainfall from trim for Nadine, convection on the coast, struggles a little bit, but then it becomes very convectively active before it gets named. The next wave actually the rainfall tends to be suppressed for quite a way and actually doesn't get named. And we're arguing that it's the dry air at low levels getting into this system which favors the development, and into this system, the dry air getting into this one that disfavors development. So moving on to longer time scales, but still in the noise, if you like, in terms of seasonal activity, and that's intraseasonal variations. This is a Hoffman showing, this is actually 1 year, just to highlight, that within a season you can get quite a lot of variability in terms of easterly wave activity. Now I'm not looking at individual waves here, I'm looking at periods of time where you get a lot of waves. This is EKE associated with wave activity. This is June to September. This is the west coast leaving Africa, so you can see a bunch of waves maybe coming through here, then it's suppressed. The initiation location of waves tends to move eastwards in this one, so this, again, suppressed here and more active here. So there is significant intraseasonal variability of easterly wave activity during a season. I'm going to highlight two coherent features that can affect that. One is the MJO, and the other one is on longer time scales, and the other one on shorter time scales is the convectively coupled Kelvin waves. I just want to show you quickly the type of signal over Africa in terms of wave activity that occurs with respect to these. The figure on the left, this figure shows you the OLR according to Wheeler and Hendon's RMM phase diagram. Each of these phases lasts about 7 days according to the phase of the MGO. This is the Indian Ocean MGO convection, which tends to move eastwards with time during the MGO. The signal over Africa is interesting in that the signal actually is often associated with a westward moving equatorial Rossby wave. So the rainfall tends to peak in this phase, while the convection is moving eastwards with the MGO. Actually, it's a westward moving component, which has convection peaking over Africa in phase 1, 2, moving out into the Atlantic in phase 3. And this is just a show and tell, really. This is EKE associated with the African easterly wave activity at 700 millibars. And I just want to highlight the fact that red is increased wave activity. So in red here, phase 1, 2, going into 3 highlights the most active wave activity associated with the MGO phases. And this also is enhanced tropical cyclogenesis phase in phase 3 going into 4, whereas in phases 5, 6, 7 you get suppression of wave activity. So MGO certainly has an influence on the rainfall over Africa and also wave activity. So that's like 30 to 70 day time scales. If we go to shorter time scales, Kelvin waves can actually impact daily weather, but also longer time scales. So Kelvin waves are eastward moving, convectively coupled Kelvin waves are eastward moving disturbances, and I'm going to show you a composite here, which highlights the movement of the dash line here shows you anomalous convection associated with the Kelvin wave over Africa. And just to give you a sense of, this is 6 days before it arrives of Africa. And the dash contours show the active phase, and you can see them moving into the coast. It lights up the convection at the coast, lights up convection further east as well. So I would argue that Kelvin waves need to be monitored for terms of convection and easterly wave activity. And just to prove to some extent that they can have a role, this is a Hofmuller showing an active Kelvin wave coming through here. During beginning of August this year, there was no wave activity. After this convective triggering system came through here, we got a lot of waves triggered. So Kelvin waves can come in and affect the variability of easterly waves for sure. And this is actually a composite of all Kelvin waves coming through. This is Kelvin waves coming through this is where it reaches the coast at day 0. But after the passage of the Kelvin wave, you tend to get enhanced EKE activity indicated by the orange shading here. And finally, just to show you a relationship between Kelvin waves and tropical cyclones, just in the interest of time, just focus on the right figure. 0 is the time that Kelvin wave passes the particular location, and we can see an enhancement in the tropical cyclogenesis frequency during this and after the passage of the Kelvin wave, which we argue is linked to the generation and enhancement of easterly wave activity. So this is definitely part of the noise within a season. Summary. Regional variations in wave structure. There's marked variations in wave structure during a season. Waves tend to intensify at the coast before they leave, and variability in these processes likely impacts the probability of tropical cyclogenesis. The most important differentiator between favorable waves that develop and those that do not is the presence or not of moist air at low levels ahead of the wave, which is a new result we're exploring. And within the season, in terms of wave activity variability, the MGO has a strong influence, and convectively coupled Kelvin waves also have a strong influence on easterly wave activity. And I just wanted to finish off, I'll just jump to this slide. We are developing a tool for monitoring the characters of waves during the season at the coast. This is a line highlighting the coastal passage, and the color coding here represents various qualities of the easterly wave, and red is bad if you're interested in tropical cyclones. Green is good. I'll just highlight this here. Green is, all these green numbers mean it's all favorable in terms of wave and the East Atlantic humidity. And in 2012, we only had 2 of those, and Nadine was one of them. So this is a tool we're trying to develop at the moment in terms of diagnosing favorable waves in real time. And I'll leave it there.
Thanks, Chris. That's really interesting. This tool, is this going to be available on your website after you're finished with the development, or what's the plan for it?
Yes, we're involved in the HS3 field campaign, so we're going to get this tool up and running, for the hurricane season, so we can start monitoring it. So we're quite excited by looking at this. It's just a quick way of deciding. Green is favorable here, orange is mid, and red is unfavorable.
Yeah, it's very nice. We just, over the course of the summer, hear about dust, at some point, and that's been suppressing. But this is a nice decomposition of a number of different factors to think about. So, anyway, thanks for the presentation. I haven't received any questions in the chat, so people, please type them in. But I'll see if there are any questions here in the room for Chris. No questions. I'll wait a few seconds in case somebody's typing something in. Okay, I haven't received anything. So, Chris, thanks a lot for the presentation. There was one more question, but since we're a little bit past time, there was a question for Kinsey, but since we're a little bit over time, I think I'll just I'll conclude. We'll adjourn at this point. So maybe that question could be asked offline. Thanks to the 4 speakers. This was a really interesting webinar with a pretty nice array of talks and topics. So thank you for taking the time to put slides together and to show up and present. Really do appreciate it. And we have another webinar coming up in late May 30th, Friday, May 30th, and it's going to expand on the drought work that you heard about today, MAP funds, the MAP program funds, monitoring, understanding, and prediction research. And we're going to hear from 3 speakers: Rong Fu from the University of Texas, Chunzai Wang from the NOAA Atlantic Oceanographic and Meteorological Laboratory, and Krista Peters-Ledard, who's at the NASA Goddard Space Flight Center. So I hope that everyone will come back, and thanks for showing up and attending this webinar today. So we'll talk to you in May. Thank you.